referencing cells in a cube, and touched upon the concepts of attributes, dimensions, hierarchies, levels, and members. We are ready to discuss queries. However, for the purpose of our examples, we are going to refer to dimensions and members, leaving out explicit references to hierarchies and levels to make notation simpler. Remember that the formula engine is going to attempt to make sense of our queries if it can do so.
Let's go ahead and try to run some queries from SQL Server Management Studio against the cube we created with PFE data. Let's connect with Analysis Services, go to the PFE demo database, that's an SSAS database, and open a query window. I'm going to go ahead and open a file of queries I have already made, and I strongly recommend that you avoid for as long as possible writing MDX in front of customers. This can be one of the most embarrassing and demoralizing experiences you can have because the punctuation is so obnoxious. Now here we look at one prototype of a possible select statement in MDX. It has some similarity to SQL Server SQL statements. In the select list, instead of a select list of table columns from a relational table, we're going to have sets of tuples, and we're going to specify the tuples that we want along the columns and the rows. Now theoretically this could go beyond columns and rows because we're dealing with a multi-dimensional structure. However, our display device is limited to 2 dimensions, so probably all you're ever going to see here is rows and columns. The sets will be sets of tuples of the same dimensionality, which means they have the same number of dimensions, that those dimensions are the same dimensions that are specified and the same dimensions that are omitted. If a tuple or a dimension is specified in the columns axis, it cannot be specified on the rows axis as well, nor can it be specified in the where clause, which is going to be a tuple which can further limit or expand upon the scope of the cube. It can expand on the scope of the cube because if it includes a dimension that has a very limited default value, we may specify another value for that dimension that is at the all level. The from clause is going to contain a cube name or a subcube specification, which may be another select statement. We will not discuss perspectives any further here, but perspectives are ways of simplifying a complex cube into something that is more manageable with just dimensions and measures that are relevant to a particular person or environment. Let's go ahead and create our first select statement. This select statement is going to be so simple it isn't even going to have a rows clause in the select portion. I am spreading this out as far as possible and starting out in a large font so that we can see as clear as possible the distinction between the different types of brackets and braces, because this is very important. Now in the first example we have here, we're going to look at the PFE cube, which is the only source we have at the moment in this SSAS database. And we're going to have a column specification, which means this must be a set. And this set is going to contain one tuple, and we are going to specify within that tuple a value, a member, for every dimension, including the measure's dimension. So let's see what happens. And in fact, we get a result showing one cell at the level of granularity for each dimension that we have specified. Now what happens if we specify something else? Let's go in and put in a different measure where we replaced number of PFEs with number of certifications, and we get the value of a different cell in the cube. Next, let's try omitting one of the dimensions. We'll not select the where clause I have here yet. And we'll see we get the same result as we did in our first query. And that's because there's a default measure which I have specified in the cube as being number of PFEs. So if we don't specify it, it's though it's there anyway. Now, if we do go ahead and put in a where clause, notice that this measures can be either in the tuple itself in select clause, or it can be in the where clause. In the where clause, we're basically saying we're looking at a cube that has a measures dimension of number of certifications, and the other dimensions are either the default values if they are not specified elsewhere, but in this case they are specified elsewhere. We're specifying all of these values so default measures don't come into play at all. Default members don't come into play at all. If we start taking out items, we'll see that we continue to get values. The column headers are not shown for the dimensions we have not specified, but we still get the same result because they have default values if they're not specified. We could keep this up almost indefinitely. Notice in this case we get 39 because the geography dimension, which we have omitted, now is going to the default geography member, which is the all member. Can we eliminate them all together? Well, at first it looks like we can't because we get an error. But that's because we have a tuple with nothing in it, and that is not defined. But a set with nothing in it is defined. It just doesn't have anything in it and returns nothing. Sorry to go to smaller font, but we have to in order to see more of the query. Remember, our column specification is a set, so we have the set designation. We have a comma between two tuples, although we could have as many commas and tuples as we wanted. And in this case, we have specified every dimension, and they are all at the same level of granularity. So let's run this, and we'll see that we get back the two cells that we expect. Now, we've been working just with columns, so let's go ahead and try one that has rows as well. We will specify two tuples in the columns axis, and that means that for the dimensions that are not specified, we would ordinarily get the default members back, but we don't get the default members back because in fact the specification gives us other values to use instead of the default members. We don't need default members for dimensions that have specifications.
In queries run in SSMS, the query engine returns more information than you see explicitly shown in the grid. By clicking on a column header or cell, you can see the information that is shown by default. A query returns metadata about the cell's coordinates and hierarchies so that a tool knows how to display the data. The tool might be Excel or some other third-party product. It is also possible to use additional syntax features in MDX to request more properties of the cells and headers. If we want to use this metadata programmatically, or other metadata that we can specify in the query, we can use ADOMD.net, a library of objects a .NET programmer can use to request specific metadata and parse the data and metadata returned by a query.
This section of the video deals with an issue that is a very important part of MDX query performance optimization, and that issue is the correct setting of attribute relationships and properties. This goes beyond the mere creation of hierarchies. Although this demo emphasizes the effect where there are multiple entities at the same level of a hierarchy with the same name, the optimization shown here is important regardless of whether duplicate names exist at the same level of a hierarchy. I am going to fast forward through the creation of a relational dimension table containing a logical hierarchy of countries, states, and cities. And populate it with some token data. Notice that at the city level there are two cities named Springfield, and although they have the same name, they are clearly different cities, and we would like to be able to analyze data recognizing that they are separate entities. I have also created a fact table named Sales Facts populated with some data, showing the same number of sales for each city, and I have declared the appropriate foreign key relationship for the tables. Let's start a new project in BIDS to see how we can optimize user-defined hierarchies. We'll create a project, select the Analysis Services project template, and give it a name. We'll create a data source that points to our relational database. That is a star schema, very simple star schema relational database. And I'm going to change this name because otherwise I'll have a project, data source, and likely even a cube with the same name. There's nothing wrong with that, but I like them to have separate names because it avoids me being confused. Next, I'm going to create a data source view that tells what from that database I want to be included. I'm going to take the region dimension table that I created and the sales facts table that I created and name those appropriately. Now, I'll go ahead and create a dimension using the dimension wizard. I'm going to use an existing table, the region table. If the table you want is not in the combo box, it may be that you have more than one data source view and the wrong one is selected. Key columns, the region ID is the key for the region table. And we're going to select all of the attributes. Notice they say we're going to surface them as hierarchies. What they mean is we're going to expose them as attribute hierarchies. And remember that attribute hierarchy is a term of art, meaning a hierarchy with exactly one attribute in it. When we refer to hierarchies in the manner that you're probably used to using the word hierarchy, we'll say user-defined hierarchy, and it will have multiple attributes in it. The name is acceptable. And now we have our dimension created. I'm going to go in and deploy and process the dimension, and we're going to browse it. We've not displayed deployment and processing to save time. So now we're going to go ahead and browse, and we'll notice that it shows hierarchy at the top, and it shows each of the individual attributes. We can tell that they are attribute hierarchies because that is the meaning of this icon, the 6 dots, by the name of the attribute. And we'll select city, and we'll see that it has Springfield exactly once, which suggests that it is not viewing the two Springfields as separate entities that happen to have the same name, that could in fact have other different names, but they don't. We'll see that the other attribute hierarchies are shown correctly because they contain unique members. Just because the dimension doesn't recognize the two Springfields as being different, is that going to preclude us from using the cube that we create in a way that we want that does show the Springfields to be separate cities? Well, let's look and see. We'll create a new cube using existing tables. We'll select the sales fact table as the source of our data. We could select either one of these measures because each one contains exactly one row with a value of 1 for each city. I'll select the measure that I created. We'll select the region dimension we just created. And now we'll go ahead and give the cube a meaningful name. We see here the cube, which looks very similar to the data source view, except the data source view doesn't have any color associated with it. It is easy to get those confused. Let's go ahead and deploy and process the cube. Again, we're not showing any deployment and processing in this video. When you do this in real life, it may in fact take a fair amount of time if you have more than a trivial amount of data. So let's go ahead and browse it. We'll come and look at the sales measure, and then we'll go to region and see that it has a number of attribute hierarchies under it. Let's select city. And when we look at city, we can tell by the results of the data that it has not distinguished the two Springfields as being separate cities or entities. But if we go ahead at runtime at query time and create a hierarchy by dragging and dropping the appropriate columns. We'll see that it does. And that's because we've now given it enough information to say that one Springfield is associated with Missouri and another is associated with Illinois, and that it makes a difference. Now, another way we could make that distinction is by coming in and showing the city, seeing that there are two Springfields, and then drilling down by state and seeing that they're in different states. This is not really as meaningful. It's not ordinarily the way we would do it. Every other city is going to be shown as existing in exactly one state. But we can go ahead and make a hierarchy however we want from attribute dimensions. And if we make our hierarchy correctly, it will show us what we want. But Analysis Services doesn't understand from the get-go that Springfield is in two states, and it can make some optimizations in its querying and in its building of the cubes and in aggregations if it has more information. Let's see how to give it that more information. Let's go back to the region dimension. We'll go to dimension structure, and we will create a user-defined hierarchy. When we drag the top level over, it gives it a default name of hierarchy, which is not very helpful. So I'll go ahead and create a hierarchy called region. We'll put state and city in the appropriate order. We'll go ahead and process and deploy the dimension. We'll browse it. We'll go ahead and reconnect because the cube has changed since we originally deployed it. We'll notice that under the hierarchy combo box, we now see an additional hierarchy, and this one is a user-defined hierarchy as denoted by the triangular set of dots. If we go to the city attribute, we see that it still views Springfield as being one city. But if we go into the region hierarchy, we'll see that it does in fact know that there are two Springfields. So let's see how this works in the cube. We'll go ahead and redeploy and process the cube. We'll reconnect. We now see that region is in the list of dimensions. Let's go and clear this. And we'll drag region to the designer window. We see that it is correctly showing the two Springfields separately, but has it really gotten any smarter? Let's try our city sales example. And we'll see that by adding a user-defined hierarchy in the dimension editor, all we've really gained is the eye candy of getting a separate region hierarchy defined so that we don't have to drag these items over individually. Now that is nice because it lets the users do things more simply and suggests how to use the cube. There are even ways that we can go ahead and hide these items from the user so that in fact they must use the hierarchy that we have suggested. This suggests that Analysis Services still hasn't figured out that Springfield is two separate cities, regardless of how we look at the data. We have to do more. Let's go back to the dimension attribute, and we'll see that after we define the dimension structure, if we look at the attribute relationships, we'll see a designer that is nicer than what was in Analysis Services 2005. that lets us go ahead and define the hierarchy, showing that the state rolls up into countries and that cities roll up into states. Now, if we go ahead and try to process at this point, we're going to get an error. And the reason we get an error is because analysis services believe we have lied to it, that it has found a duplicate value under Springfield, under the city, that does not roll up appropriately into states. So we're going to have to do more to tell it at this point that this is in fact a valid hierarchy, but that it's going to have to look at things a little differently. We do that by selecting an item in the hierarchy and going to the Properties window. When we go to the bottom of the Properties window, we'll see the Key Columns and Name Column properties. Under Key Column, we'll click on the ellipsis and see that it is saying that the key for state is the state column, that uniquely defines it. In our case, it does, but we want to create a more intelligent hierarchy that perhaps includes the possibility that there will be multiple states in different countries with the same name. And even if there aren't, this operation permits optimizations for querying and aggregation. So let's go ahead and create the hierarchy. We've said that the key columns are now country and state. When we set the key column, we must then set the name column. And that says that even though the hierarchy is country and state, we would like to have the name shown at that level for its members as the state. Likewise, we'll go to the city, show its properties, and say that its key columns are country, state, and, putting in the correct order, city. Its name column is city. There's one more thing we have to do. We have two Springfields, and in this hierarchy, the Springfield from Missouri is definitely different than the Springfield from Illinois. However, suppose we had a hierarchy of salespeople, and a salesperson associated with one, say, state, might at some point be associated with a different state. In that case, we would have the same salesman associated with different states at different times, but it is the same entity, the same salesperson. We have to tell analysis services a little bit more about the relationship between these items. So I'm going to go in and double-click on the arrow here and say that this is a rigid relationship, that the state is always going to be associated with the same country, and that if we have another state, it's not that the state has moved to a different country, it's that it's a different state. And we're going to do the same thing here and say that Springfield can't up and decide to change from one state to another. If this was in fact a salesman associated with the state, it would be flexible because the salesman might later be associated with a different state. So we've set the property for relationship to rigid in this case because it's appropriate. We have gone ahead and set the attribute relationships through the graphical designer and set properties through the properties window. Users very often get to this level where they have created the hierarchy and assume that the rest of the intelligence is automatically used by SQL Server to optimize the queue. That is not the case. I've had several engagements where there's been bad performance, and all we do is go in and show the user how to set attribute relationships and the properties for that those attribute relationships. And the performance increases dramatically. Let's go in now and process the dimension again. Go to the browser, reconnect, go to the city level, and we'll see that Springfield does in fact exist twice. So it is now recognizing Springfield as
two separate entities. Our cube, once we process it, will now show Springfield as two separate cities, which is as we wish. If you are new to MDX, I recommend that you do not start with the standard SSAS projects and databases based, say, on AdventureWorks. They are very complex because, in one project, the designers attempt to be able to demonstrate every conceivable feature of SSAS and MDX. Instead, I suggest that you create your own star schema relational database with one fact table and one dimension table. You only need a few rows of data to get started. Be able to create your own SSAS project, deploy it to create an SSAS database, and process it to populate it with data. Make your own queries, starting with the simplest thing you can think of that you can get to work. Then edit your dimensions to add attributes and make user-defined hierarchies, create attribute relationships, and set attribute properties, and add further complexity from there. We've come to the end of the presentation. Have you figured out why a where clause in an MDX select query doesn't have a relational operator, usually an equal sign, like a SQL select query does? If a where clause looks like this, it corresponds to saying this, although this is not valid MDX syntax, because the tuples are including the dimension with the value it takes on.